All right, let's start. Good morning. So I'm going to take attendance today. We have a couple of things to discuss regarding continuity. We're slightly behind schedule compared to the schedule on the syllabus, but it's not a major issue. Now, in principle, you're responsible for what we're going to discuss this week, but certainly you should be focusing on the contents of the problem sets. So far in the problem sets, you haven't studied continuity, so that means that you should first and foremost study the topics in the previous problem sets and other things that I mentioned in the guide that I uploaded on Friday. But if you have extra time, certainly you should be focusing on continuity and stuff like this as well. Ultimately, you're going to be responsible for continuity, but it's not a sort of priority. It shouldn't be a priority for you. So me and the grader, we're going to try to release the grades for problem set by Friday so that you have some time in the selected solutions and everything. I should ask, are there any questions about the midterm? Yeah.
Where is the guide uploaded?
Oh, it's on there. It's on Canvas. So if you go to the Assignments tab, there's an assignment for midterm 1.
Oh, okay.
Yeah. And then once we're done with the midterm, I'm going to upload the key there as well. Okay. Any other comments or questions? I'm not going to do I'm not going to take a class to do a review, but I'm more than happy to meet up if you want to discuss things. So, continuity. So if I have two metric spaces, right, two sets with their own notions of distance, x and y, and if I have a function f from x to y and a point x star that is specified, then I get to define what it means for this function to be continuous at this specified point. I should also mention I'm almost done editing the footage from last week. Hopefully by the end of today you're gonna get that as well. Okay. So if it's continuous at x star, how I defined this was I gave two conditions. And I said, these are in fact equivalent, even though they may not look like it. One of them is, in terms of sequences, it says any sequence that converges to this specified point under f transforms into a sequence that converges to the image of x star. And then another definition was this epsilon delta definition. And so, for instance, here, d sub capital X really means, even though I didn't state it here, d sub capital X is the distance function defined on the metric space X, and d sub Y is a distance function on Y. In any event, I said that these two are equivalent, but we need to verify this. So the claim is really about this equivalence. And we'll do that today. I'm not going to prove it for the general metric space case. I'm going to just focus on the case when x and y are subsets of the reals, and I'm going to leave the general case to you. It's literally the same argument. It's just that you need to use this notation instead of the absolute value notation. Okay. Before I get to the proof, here's a couple more definitions. I had defined this also. Once we have continuity at a point, we can talk about what it means for a function to be continuous at large, or just continuous, if it is continuous at any point, okay? And once you have that, you can define this set C0 of x, y to be the set of all functions from x to y that is continuous. So this is our first function space I told you. Right now it's just a set, but once we start talking about convergence of sequences of functions, typically we're going to be taking that sequence of functions from here. And we're going to want to have the limit to be continuous and stuff like that too. Typically, we're not going to look into this, but rather we're going to choose y to be reals. X really doesn't matter. It doesn't matter that much what x is, but the outputs we want to be reals. And so In the case when y is r, I'm going to define this new set, in fact. C0 sub b, x to r. Well, this is going to be the set of continuous and bounded functions. So I can just write it like this. It's the intersection of all continuous functions, it's a set, together with the set of all bounded functions. We define what this means. This is a set of all continuous and bounded functions. You can define boundedness in an abstract metric space, but we're not going to need it, so I'm going to leave it for now. What else? OK, I'll also remind you what this turns into when x and y are subsets of the reals. So if x and y are subsets of reals, then two, how to say, can be rewritten perhaps. Can be rewritten as, well, for any epsilon, there is a delta such that for any x in x, well, let me be clear about the quantifiers actually. For any epsilon positive, there is a delta positive such that for any x in x, if the distance between x and x star is bounded by delta, then the distance between f of x and f of x star is bounded by epsilon. Okay. I just wrote down, I just substituted this instead of this more abstract d notation. I just said, oh, in this case, my distance function is this very nice concrete thing. I can just replace it. That's what I did. In case x is an interval, okay? And in fact, let me say, in case x is an open interval, I'm going to introduce one more notation that corresponds to continuity. If x is an open interval, so in this case, you can think of it like this, but I'm assuming more about x. We also write well, here's the idea. Instead of taking two distinct points, x and x star, and saying that the distance between them is at most delta, you can just, instead of using an x, you can use a number of the form x star plus h. So you want to think of it as, oh, h is a small perturbation of x star. And so instead of saying, oh, this is the distance between two distinct points, you can say, for a small perturbation, the outputs are close, and we write it like so. F of x star plus h equals f of x star plus little o of 1. Little o of 1, and underneath the little o, you write h goes to 0. Okay? This is how you read it. F of x star plus h equals f of x star plus little o of 1. Okay? That's how you read it. Okay. There's a definition that we're going to discuss later. For now, you can take the definition of this whole thing to be this whole thing. Okay? This is hidden right now, but this 1 inside you see here actually is h to the 0. And the reason why we use this symbol, c to the 0, for continuity is also why we're putting h to the 0 here. So in a sense, continuity you should think of as functions that you can approximate up to 0th order. Now later on, after we discuss this differentiability, well, the differentiability is going to be, for us, functions that can be approximated up to 1st order. Okay? So later on, so C1 is going to be what we're going to call continuously differentiable. It's going to be the collection of all continuously differentiable functions. And so this means that these are functions that are differentiable, and furthermore, their derivatives are continuous themselves. Okay? And we're going to start talking about this very important result called Taylor approximation. It turns out that for C1 functions, instead of having 0th order terms only, you get to write it like so. This is your 0th order term. And then we're going to define this f prime, the derivative function, times h, plus we're going to say little o of h to the 1 as h goes to 0. Okay? So this is the idea of Taylor approximation. This is going to take us quite a while to get to, but we're going there. Then we're going to put C2. We're going to have a 2nd order term. Then we're going to have little o of h to the 2, and so on. And then we're going to take this exponent to infinity. We're going to have C infinity. And then we're going to go one step further, in fact, in the last part of the class, where we're going to realize, well, if you keep doing this, you end up getting sort of an infinite sum. And we're going to start worrying about whether or not that infinite sum actually converges. And that's going to lead to this theory of real analytic functions. Okay? So this 0 is signifying all this at this stage. Okay? We're already sort of transitioning. We're orienting ourselves toward calculus and approximation. Okay? For now, we're not going to need it. But in case you're sort of somewhat concerned or confused about where this 0 comes from, this is where it comes from. Then if you take more advanced classes, then you start looking into negative exponents here as well. But we're not going to do that. Okay. Any comments or questions about any of this so far? Yes?
For the red color in the middle panel,
Yes.
it's a big X.
Um,
Small X.
You mean this one?
Correct, right. If X,
Capital X is an open interval.
that is the domain,
Yes.
and then you still have an element called X.
Star. Yes. So at this stage, X could be a bunch of X could be a finite set of numbers, for instance. Or it could be an infinite set, whatever. In principle, this X could be the set of integers if you want. Up until here. Everything works. But for this notation specifically, I'm requiring that X be an open interval. So that I am guaranteed that for sufficiently small h, x star plus h is still within x, so that this left-hand side is defined.
So you don't write epsilon anymore.
Exactly, yes. That's the thing. So this little o notation compresses all these. And so now it becomes like a higher order thing. But this is perfectly equivalent to this statement.
But you still need to write delta, right?
this expression includes all of this, packages everything into one thing, makes things very convenient. Okay? So we started with the assembly code, okay? So we started with zeros and ones, but as time goes by, we need to be able to sort of black box a bunch of things. So every time, for instance, that's part of why we're sort of proving theorems as well. Every time we're proving theorems, in principle, you don't need to prove anything. You can, or you don't need to sort of refer to a theorem to do something. Instead of referring to the theorem, within whatever proof you're doing, you can just take a second, prove whatever theorem you're trying to use, then keep going. But the point of establishing something as a theorem is to black box it. Okay? So that's sort of how technology works in a sense. So as time goes by, our sort of concerns get more involved. And certain things, even though, foundationally they're pretty much the same, they're made of the same things, we want to think of them as black boxes. We don't want to worry about how it actually operates. We abstract out. Okay? So when you're using your tablet, for instance, you don't want to worry about the transistors in it in this specific instance. There is someone out there who's worried about transistors in tablets, but not for you. Okay? Not here. Or, I don't know, it's like the chemistry of the ink in my marker. I don't want to worry about this right now. Does that kind of make sense?
So this small I can be written completely by this red.
Exactly. This is completely equivalent to this. Yes. Exactly. Yes. Any other comments or questions? So this is part of the difference between a lower level calculus course and this course. It's like in a lower level course, they tell you and maybe they try to justify why certain things are true, but you don't dig that much into why things are true. Or you're not really worried about establishing them. Here we are worried about these kind of things. And there are also times when we study theorems, we study the proofs of theorems, and then maybe there's a different situation where the theorem doesn't exactly work, but maybe you can sort of open up that black box, reverse engineer certain parts, combine it with some other theorem or the proof of some other theorem, and maybe you can come up with something new. Okay. So let's prove this. Prove that this statement is equivalent to this statement. Like I said, I'm not going to use this more abstract notation. I'm going to leave that part to you because it's a very good exercise. I'm going to do it for the case of reals. So I'll just do it like this. So exercise. Prove blue star for general metric spaces. Like I said, what I'm going to write down, pretty much verbatim going to work. It's going to pretty much verbatim work, but you're going to have to use this notation instead of this absolute value notation. That's the only difference, really. In the past, because of this, I just stuck to this notation, but I think it'll be much more useful if you use this absolute value notation. Proof of blue star for the case of x, y subsets of reals. Okay, so I have two subsets of the reals. I have a function from one to the other one, and I fix the point in the first set. Let's start with 2 implies 1. Right? So for equivalence, I need to show that 1 implies 2 and 2 implies 1. So now I'm supposing that item 2 is satisfied. You can think of it like this as well. What do I need to show? I need to show that if I were to take any sequence that converges to x star in x, then the image sequence 2 converges to f of x star. Okay? So what do I need to do? I supposed this statement, or this statement. Now I need to show this. To show this, I need to take an arbitrary sequence in x that converges to x star. So let x bullet converge to x star in x. Let x bullet be, well, let's be a little bit more explicit perhaps. Be a sequence such that no, I'll just write this notation. X bullet converges to x star. Okay. Now, I want to show that f of x bullet converges to f of x star. Let's write that as well. Okay. Opening up the definition, just to remind ourselves, for any epsilon, there is a capital N such that for any lowercase n after capital N, well, the distance between the nth term, or rather the image of the nth term of x bullet under f, is within an epsilon of this guy. So, now this is what I'm trying to show. So let epsilon be positive. Okay. I assumed that this epsilon delta definition holds, which means for this specific epsilon that I chose, there is a delta such that this whole thing happens. Then by 2, which I had assumed, there is a delta such that for any lowercase x and uppercase x, if x and x delta, x star is at most delta apart, then I am guaranteed that f of x and f of x star is at most epsilon apart. I just opened up and wrote down what I had assumed as item 2. But now, we had assumed that x bullet converges to x star, which means, since I'm given a delta, I know that after finite time, the distance between these two guys is going to be within a delta. Okay, so dagger, continue here. I'll write it here because I want to keep the statements. Continued from dagger. Since I assume that x bullet converges to x star, using this specific delta as my error margin, I know that there's a capital N such that after that capital N, these two guys are at most delta apart. Okay. But if it is the case that for all lowercase n after uppercase n, in other words, if for all lowercase n after uppercase n this happens, this is the same thing as saying that the capital N tail of x star, x bullet, is within x star. Which means that for each such term, I can apply this. Let's call this red heart. Okay. By red heart, because for all lowercase n after uppercase n, this is satisfied. This has to be satisfied also. Then by red heart, this has to be satisfied, and that is the definition of what it means for f of x bullet to converge to f of x star. Or maybe I shouldn't put a box here because we have the other side. But we're done with this side. That's the end of this side. So you see, we're now starting to sort of chain multiple logical statements to get something more. Okay. Any comments or questions about this part so far? So far I showed that epsilon delta definition implies a sequence definition for continuity. For the other side, I think the easiest method is to argue contrapositively. So maybe I should say, so that f of x bullet converges to f of x star. For 1 implies 2, I'm going to argue contrapositively, which means that I'm going to assume that item 2 is not satisfied. And I'm going to try to argue that if item 2 is not satisfied, then item 1, 2 cannot be satisfied. We'll argue contrapositively. So suppose not 2. Suppose 2 fails. I think I'll continue. I'll just erase these two things. And while I'm erasing, try to think about what the negation of that statement is. I'll just draw an arrow like this. What does it mean for 2 to fail? That means that there's a delta, there's an epsilon such that for any delta, there's an x such that x is within a delta of x star. However, right, the implication fails. These two are at least epsilon apart. So I'm not going to go through this negation again. when you negate it, it turns into this. There is an epsilon, 0 in fact. All right, because it's a fixed epsilon I want to think of. For any delta, there is an x such that x minus x star in absolute value is at most delta. However, this fails. But f of x minus f of x star is not less than epsilon, but the other way around. Right? So the implication fails, I want to say. How did I do this? Let's reiterate. Okay, there's a bunch of quantifiers here. You keep the order matters, you keep the order. For all turns into there exists. There exists turns into for all. And then I have a statement. A implies B. How could it fail that A implies B? Well, if A happens but not B. Therefore, I have to do this. That's the negation. Okay. Now, the issue is this, okay? We started with supposing that 2 fails, and somehow we need to argue that 1 fails also. What does it mean for 1 to fail? Well, again, negating whatever, to display that in this case 1 fails, we would need to be able to construct a sequence that converges to x star. However, its image fails to converge to f of x star. So I need to construct a sequence. And so this is a very useful method that I'm going to use now. I'm going to take this statement and I'm going to farm it, okay? I'm going to farm it to construct a sequence. I'm not going to do anything with epsilon 0. That is fixed. I am allowed, however, to choose delta as small as I want. And that's what I'm going to leverage. If I were to choose delta to be 1, the statement says there is an x sub 1, let me say, because that specific x depends on the delta you chose, such that this happens but not this. So for delta equals 1, there is an x1 in x such that x1 minus x, oh, maybe I should say, oh, okay, that's fine. x1 minus x star is at most delta in absolute value. However, f of x1 minus f of x star is bounded from below by epsilon 0. Now, I keep shrinking my delta. In this case, you don't need to worry too much about how to shrink. There are other situations where you need to worry about how fast you should be shrinking and stuff. In this case, we can just take whatever sequence that we know converges to 0, for instance, 1 over n. So for instance, then I can say for delta equals 1 over 2. Oh, in fact, I probably should be a little careful. No, it's okay, actually. Okay. Delta equals 1/2. There is an x2, again by the same statement, such that x1 minus x star, and of course this delta is supposed to be 1, and this is x2. The distance between x2 and x star is at most 1/2. However, f of x2 is at least epsilon 0 apart, again by the same statement. And you keep going like this. Delta equals 1/3, 1/4, whatever. We can just say by induction, for any n, there is an x sub n and capital N such that x sub n minus x sub star is at most 1 over n distant from each other. but f of x sub n minus f of x star have to be far apart. Epsilon is some positive number. I don't know how small it is, but I know that it is not 0. Consequently, x bullets is a sequence that is well defined. It's a sequence that is in x, converges to x star, okay, because the distances converge to 0. However, the image stays far apart from f of x star. That's what it means for x bullet to converge to x star, but not its image. So you can just write it like this, and then put a dash to signify that the convergence fails. So this guy doesn't converge. And that's now the end of the proof. Okay. So this method ends up being very useful. Take like a statement like this, logical statement, and then you start farming it, or that's what I call it. You start sort of like picking certain values, and sort of you engineer sort of like a decreasing sequence that gives you something with a bunch of properties. You have to be a little careful about how you're fixing these deltas and stuff like that. But this procedure I call farming. So this. You plant something and then you start farming it to get something more actionable. Comments or questions about this? Yes?
Are we all talking about sequence now?
What do you mean?
At a single point? On the claim, right?
Yes.
You have a function, right, from a set x to a set y.
Yes.
And then have an x subscript star
Yes.
is a number?
In this case, it's a number you can imagine. Yes.
Not a sequence.
No. X star is not a sequence. X star is a fixed point. I'm asking whether or not f is continuous at this fixed point.
But all these proofs seems to prove sequence.
Well, I am using sequences that converge to this fixed point. So when I wrote this, I meant so this first item says, for fixed f and x star, f is continuous at x star if for any sequence that converges to this fixed point that I chose, the image sequence converges to f of x star.
So f x star is also a real number.
Yes, these two are fixed points, exactly.
Okay.
This is a sequence, this is also a sequence. But this sequence is an arbitrary sequence. Comments, questions? Yeah, it does get confusing what is arbitrary and what is fixed and stuff. And my professor used to use the phrase arbitrary but fixed. And I used to hate that. And like, after 5-6 years, I realized, I get what that means now. So, but yeah, it is confusing. I can relate. I've been thinking about this too. It's like your questions often, it resonates with me, these questions. But somehow, I seem to have forgotten when these things actually made sense to me somehow. It's like, it's very bizarre. It's like, I remember the times when I was confused and I had similar questions, but I just think differently now somehow. I guess that's like indoctrination or something. I don't know. Yeah. So for instance, like, I should mention this. Probably this going from here to there is something like an axiom of countable choice or something like that. There's like a bunch of logical things that I'm not really familiar with. But, you know, we're not going to worry about those kind of things. Most people would agree that this is a valid proof, and in the textbook they give this as well. So, not doing anything dissonant. Comments, questions? Yeah.
So the reason you can do the whole farming thing is more or less because the order of the quantifiers is different. Like you can fix your epsilon, and then because of that, you can just like, there's so many different.
Yeah.
So I wouldn't have thought of that personally.
Yeah. And again, like I said, it's like for some people, these logical quantifiers are more confusing. They just like using the, you know, simple English versions of these statements. And you can. It's like you can just write it like this. For any epsilon, there's a delta such that if the distance between these two things is at most delta, then this happens for any x and x whatever. Like in the textbook, there are like these like more verbose statements. In my estimation, they're like longer to write down, more fuzzy. I just find it more convenient. I don't even think about how to negate things at this point. For me, it's an algebra operation. I just distribute the knots, keep the orders of everything, turn this the other way around, turn this the other way around, and so on. For me, it's an algebraic thing. What is the opposite of something? Often, people who are using sort of simple English statements, they end up needing to sort of think about what the opposite of something is, in my experience. But then, of course, the downside is that you need to be careful about the orders of things. You know, you need to be careful about writing things down and so on. It all depends on your style. And I think I received an email, and I think that's what your colleague was asking. In the exam, just because I'm using these symbols, you don't need to use them, okay? If simple English is better for you, then use those. But of course, if you make a mistake, you know, in either sort of style, that might cost you something. Okay. Part of this course is, you know, experimenting with what works for you. In a sense, it's like this course is a little bit about just like any other math course, as far as I'm concerned. It's about realizing how your brain works. So you test it out. Where exactly are your strengths? As far as I'm concerned, as humans, we like to want to be strong in this and not that, and we would like to sort of imagine. But when it comes to, you know, when it comes to the reality of things, you realize, oh, you know, I'm good at this thing and not that. Anyway, any other comments? Or, yes, go ahead.
Do you consider the bullet point I mean second one, the dx and dy is also a sequence or just?
This is a function which is the metric on x.
Right, and because x is a sequence and x.
Here, no, this x is not a sequence. Okay. This is a sequence, x bullets. I told you, I use bullet notation for sequences. If it's not a bullet, there is no sequence. That's the thing. The first statement uses sequences explicitly. In the second statement, there is no sequence. Okay? But somehow, even though these look very different, they are equivalent to each other. That's what I'm saying. Okay. For certain situations, the sequence definition ends up being more useful. For certain other situations, this epsilon delta ends up being more useful. And there are a couple more statements equivalent to continuity. One of them is about like oscillation, for instance. You're gonna probably see this statement, function is continuous at a point if its oscillation, which is a specific term, is 0 at that point. Doesn't sort of oscillate too much. Okay. Okay, I have about like 5 minutes. I'll just erase this part. We have talked about a bunch of examples of continuous and discontinuous functions, so I'm not going to spend more time on these. I'm going to keep marching on. One definition that is important is a homeomorphism. Okay? Homeomorphism is, well, basically something like a bijection, but you also include the notion of continuity in it. X and Y, the metric spaces. So I'm going to keep defining things in this more abstract context, but if you're worried about this metric space notion, you can just consider X and Y to be subsets of reals. Doesn't matter. Homeomorphism from X to Y is a function from X to Y is an f from X to Y such that, well, f is a bijection, or maybe I should say f has a functional inverse f inverse exists as a function, and both f and f inverse are continuous. So f is continuous in the forward direction, and in a sense, it is also continuous in the backward direction. And the set of all homeomorphisms from X to Y is denoted by homeo xy. If y is equal to x, instead of writing homeo xx, people just write homeo x. Homeo x. Very nice. The remaining 2 minutes, I'll show one result about continuous functions. Namely, if you were to take two continuous functions that are both continuous, then the composition also is continuous. Now, for instance, for this statement, using epsilon delta takes longer. So I'm going to leave it to you, and I'm going to use a sequence definition. I'll just write it like this. I have a function from x to y and another function g from y to z. If f is c0 and g is c0, if both of these are continuous, then so is the composition. And the proof is, well, you take a sequence that converges in X, push it using F, then push it using G. And that's the end. I'll leave the proof of this using epsilon deltas to you. That's an exercise, and that's the end. prove using epsilon delta. OK, we're done for today. Thank you. I'll see you tomorrow. All right, let's start. Good morning. So today we're going to keep working on continuous functions. Continuous functions have essentially 3 theorems that we need to worry about, that we need to know. One of them is the maximum principle, or you might have heard the name Extreme Value Theorem. The other one is the Intermediate Value Theorem. And then the third one, well, it's essentially like a combination of both Extreme Value Theorem and Intermediate Value Theorem that basically tells you something about that makes some connections between continuity and monotonicity somehow. Probably we're going to give the proofs of the Extreme Value Theorem and the Intermediate Value Theorem today. Tomorrow we're going to look at this third theorem. And then we're going to start looking into convergences of sequences of functions and in which senses they can converge and so on. When we switch over to sequences of functions, so you see, we still haven't defined this, but this set of all continuous functions defined on an interval taking real values, right? That's what this means. That for us is going to be something like a metric space also. This by itself is not exactly a metric space, but if I were to put a B here, which in a second we're going to prove you don't need to put in this specific case, does turn out to be a metric space. There's going to be a metric on this space of continuous functions, and we're going to think about continuity, or rather, we're going to think about convergence of sequences of functions, continuous functions, for instance, with respect to this metric. So we're going to do a bunch of things. That's part of the reason why I'm already introducing this notation, because I want you to think of this as a very nice sort of thing. Okay? So here's first an exercise. If I have a metric space X, 2 functions, f and g, defined on X, taking real values that happen to be also continuous. Right? So this is what that means. And if I have a constant, alpha, then f plus g, alpha times f, and f times g are all still continuous functions. So you can add 2 continuous functions, and the sum is going to be continuous, and so on. And you can also divide insofar as the denominator is never 0. And when you divide 2 continuous functions, the ratio of function 2 is going to be continuous. I'm going to leave this to you to verify. It's a nice exercise. Let's not worry about this definition for now. We're going to get to that in a second. I want to focus on the maximum principle. Another name for this is the Extreme Value Theorem. And the idea is this. If I have a closed and bounded interval, well, from here to there, let's say, and if I have a continuous function defined on it, by that I mean, of course, the function has to be defined on the endpoints also, so you don't get to have vertical asymptotes. Okay? Then this function, no matter what this function is, at some point attains its max and attains its min. Okay, so that's the max, that's the min. Okay. Of course, in this picture, I drew a function that has a unique max and unique min. And when I talk about max and min, of course, I mean global. Right? So this, for instance, would be a local max, but I'm talking about global max. It could be something like this. It could also be something like this. Let's say, maybe the max is attained at multiple positions. That can happen. I'm not saying it attains max and min at exactly one point. It attains at least at one point. Okay? And so this is somehow related to this idea of, well, the graph of a continuous function is something that you can draw without lifting the marker off the board. Right? That's kind of the idea. one of the ideas. Intermediate value theorem is perhaps more related to that. Have you guys seen something like this before in calc? Yeah. So we need to prove it now, as usual. As you see, we're sort of transitioning to calculus. Again, I still would suggest that continuity is too flexible for calculus purposes. For calculus, I want things like differentiability and integrability and stuff like that, or other integrable functions. And even though continuous functions are integrable, continuity, this world of continuous things and so on, it's a lot more sort of flexible for me to call it proper calculus. In any event, it's certainly related, so we need to study it. OK. So here's a proof. Oh, let me state it. Right? So if I have a closed and bounded interval and a continuous function f, continuous function defined on I taking real values, then item 1 is f is bounded. So its image is a bounded subset of the reals. And furthermore, its max and min exist. Okay. So maybe we can try thinking about a case where one of these gets broken, trying to perturb the situation. So if I had an open interval, certainly I could have like 1 over x type of a situation. Okay, so this would be 1 over x defined on 0, 1, 0 not included, 1 included. This is not closed. This function is continuous. All the functions that you know to be continuous are continuous. But as you see, this is not bounded. Okay? But this doesn't say anything that contradicts the statement because this is not a closed interval. Okay? So you have an asymptote, you have a blow-up. And it's also the case that the max doesn't exist for that reason. In this case, the soup also doesn't exist as a real number, but never mind. Now, at this point, you see this duo of closed and bounded as adjectives for intervals. You see, we have seen this before, once more, in the case of Bolzano-Weierstrass. There, too, the hypotheses were, well, I guess not in that, but the nested interval property. Sorry. We had this nested interval property. We took a non-increasing sequence of intervals, and we required that they be both closed and bounded. So somehow this is also related to Bolzano-Weierstrass, but that relationship probably I'm going to leave to you to discover in the next problem set. So closed and bounded, okay? That's important. So proof. Item 1. Well, what do I need? I need some number such that for any x in I, f of x is upper bounded by m, or maybe in absolute value upper bounded by m. Well, let's say it's not bounded. Okay, negating, I have then the following. So, for any m, there is an x in I such that f of x in absolute value is greater than m. That's the negation of what it means for f to be bounded. Well, I can take this statement and farm it the way we did it, the way we did yesterday. I can say, let me let m to be equal to 1, then 2, then 3, and so on. For each choice of m, I'm going to be given some x, which means that if I were to keep taking different m's, I'm going to generate for myself a sequence in I by farming this statement. Then I'm going to have to do something with that. I'll do it once again here. Okay. Yesterday, when we were farming, I took epsilon to be smaller and smaller. But this time, I'm going to take m to be larger and larger, because that's what I'm sort of trying to manage. There's an x1 in I such that this is greater than 1. Let's do something even fancier a little bit. Once I have this x1, I have this specific value, which is a positive number, which means that as m, I can take this. There is an x2 in I such that f of x2 is strictly greater than this no m, which I know to be greater than 1. So once you have an x1 like this, so that you have this number, well, that you can plug into the logical statement you're trying to use. Then you keep going like this. Thus by, so keep going like this. Thus by induction, there is a sequence in I such that for any n, f of x n plus 1 in absolute value is strictly greater than f of x sub n in absolute value. Okay. Any guesses as to how I can proceed at this stage? So far, I haven't used. So when you're sort of trying to understand a proof, a good strategy is always, okay, so someone's like writing stuff. So if you get stuck, you can look back at the theorem, look back at the hypotheses, and see what you haven't used so far. We haven't used, for instance, the fact that f is a continuous function yet. We haven't used anything about the nature of the interval I also. What can I say here? Another thing, of course, is to think about the theorems that we have proved so far. We have one sequence here. Regarding sequences, we have essentially two theorems, monotone convergence theorem, but I don't know how these x bullet sequence sort of looks inside I. Maybe it's sort of jumping around. I don't know much about it, but I know because of the fact that each of the terms of this x bullet is in I. Since I is bounded, x bullet is bounded. Okay, I can do something about bounded sequences. What can I do with them? If I have a bounded sequence of real numbers, what can I say about this?
There's a least upper bound and greatest lower bound, essentially?
Yes, they exist, but I want something more. I want a theorem. Any bounded sequence of real numbers has a convergent subsequence. Okay, so I cannot really say much about this, if this converges or not, but I can sample out a subsequence that is going to be guaranteed to converge. Why would I want that? Because then I could use that in tandem with the fact that f is continuous, which I know continuous functions preserve convergent sequences. So that's what I'm going to use. By Bolzano-Weierstrass, X bullet has a convergent subsequence, let's call it Y bullet. Okay? But then f is continuous, which means images of terms of the subsequence is going to be a convergent subsequence, or rather convergent sequence in reals. Since f is continuous, this is like a faster way of writing f is continuous, whatever. You can just write f is in C0. This is how people typically use these kind of things. They would just like suppress the domain and codomain, because what really matters is the so-called regularity of this function. This is a continuous function. It's not a mere, arbitrary function. It has a certain property. Is convergent. But that cannot happen because of this property. A contradiction to, let's say, blue star. So this is the proof of the first part. I suppose that f is not bounded, and I came up with a contradiction. Okay.
Could you walk through a little bit more how it's a contradiction? Like, what exactly contradicts each other? Not just a little loss.
Mm-hmm. Yeah, I can be a little bit more explicit. So what does this mean? This means there is a j, strictly increasing function, such that for any n, y sub n equals x sub j of n. That's what it means for y bullet to be a subsequence of x bullets. Okay? I'm saying this has to converge to something. So there is a y infinity, and this in fact has to be inside the interval, such that y bullet converges to y infinity. And because of this, it must be the case that f of y bullet converges to f of y infinity. Okay? Using the continuity of f. Okay so far? Why does this contradict blue star? Well, because of the following. Since I constructed this x bullet sequence to be so that the sequence of the absolute values of the images of x bullet under f is a strictly increasing sequence, which means the same property is satisfied by these guys also. So if this converges to this, if you want, the absolute value of this also converges to this. But this guy is a strictly increasing sequence that in fact I can even do this. I'll add here 1 plus, plus 1, and so on. So that going back, m equals 1 gives me an x1 such that this happens. Then I choose m equals 1 plus this guy, which gives me an x2 that is more than 1 apart. Okay, and so on. At the end of this, therefore, I can say that this is infinity. But once you have this, for the specific sequence that goes to infinity, imagine something like n squared or something. No matter how I sample out a subsequence, any subsequence is going to go to infinity again. But this is saying this doesn't happen. This says that this converges to a finite number. That's the contradiction.
We're saying f is not bounded, so that x-bullet sequence
Yes.
is not bounded, right?
No, the x-bullet itself is bounded. X-bullet sequence is a horizontal sequence inside I. Okay? So x-bullet, let's imagine this. Horizontal is your I interval. It's a bounded interval, 0, 1, or 1, 2, whatever. X-bullet lives here. Okay, keeps jumping around. I use Bolzano-Weierstrass to sample out a convergent subsequence. So now, even though initially this x-bullet maybe didn't sort of stabilize at any point, I sort of got rid of a bunch of points such that this happens, okay? Converges to this point. But then what I do is I look at the images. I look at the heights associated to each of these horizontal values given by f. But I chose this x-bullet sequence in a specific manner so that when I look at the heights that f associates to each of these horizontals, I am guaranteed that the heights blow up. Okay? I made this so that the farther I go in time, the height, the higher the height gets, which consequently means this cannot happen. Because f is continuous means, remember one of the two equivalent conditions, any convergent sequence has to be transformed to a convergent sequence. So this green subsequence that converges under f by continuity has to converge, has to transform into a vertical sequence that converges to a real number. But on the other hand, by construction, the images cannot converge to anything. They blow up. And that's the contradiction. Does that kind of make sense?
It makes more sense.
Yeah.
I'm going to have to look into it more later.
Yeah, OK. I'm happy to discuss later, too. Yeah. Yeah, there are a couple of stages to this course. You sort of come to class, and that's why I'm requiring that you guys come to class. It's like someone does things, someone gives you the arguments. At first, maybe it doesn't make sense. That's layer 1. Layer 2, it makes sense, but you say to yourself, I wouldn't be able to come up with this argument. And then eventually you're like, oh, yeah, this is the obvious thing to do. But yes, like this is the natural progression. Everything is natural. The things you feel. Any other comments or questions about this part? Okay. Another good method would be, when you see a theorem, instead of starting to read the proof, well, try to draw pictures, try to come up with sort of situations where the theorem would apply, would not apply, and eventually you might also try to prove it. Right? Just without looking into the proof, like try to figure out how you could prove something. So it's like reading math literature is somewhat different than reading like regular literature, let's say. You have to keep fighting with the text. Okay. So that's item 1. Item 2, we need to verify that the max and min exist. So I'm going to erase this. We showed by the end of item 1 that f is bounded, which means that its sup exists by the completeness axiom. Okay? The point is, we need to be able to come up with some point x in I such that f of x is exactly the sup of f. By I and the completeness axiom and CA, alpha, which is sup of f, is a real number. It exists. Okay. Let's first focus on max. What we want. We would like to be able to display at least one, let's call it x star. There is an x star in I such that f of x star is alpha. That's what it means for max of f to exist, remember. Because max of f exists if sup of f exists and is in the image. That's the definition. So. Okay, that's the definition of what it means for max of f to exist. And likewise for min, I'm going to need to look at the inf. Let's first focus on the max. Well, since alpha is the sup of f, I can come up with a sequence that is, in fact, if I want strictly increasing, that converges to alpha. There's a sequence y bullet in reals, or rather in the image of f, such that y bullet is strictly increasing and converges to alpha. How can I come up with a sequence like this? Well, I could say something like this. Alpha is a soup. For epsilon equals, let's say, 1, there is some y sub 1 that is strictly greater than alpha minus 1. Then I essentially, again, farm in a similar fashion. So just to give you an idea, I'm not going to write it down, but I'm going to draw the picture. Say this is my interval here. Here is the alpha, it's a height. Well, let's say I take this lesser value. I know that there is some y sub 1 that is in between, that is in the image. But then I can take this height and say, oh, because y sub 1 is strictly less than alpha, there's some y sub 2 that is even closer to alpha, and so on. That's how I can come up with a sequence that converges strictly, that increases strictly and converges to alpha. Okay. I'm just farming the definition of alpha to be the soup. But since this y bullet is a sequence in the image, that means that for each n, there is some x sub n such that y sub n equals f of x sub n. Since y bullet is a sequence in the image, in principle, there could be multiple x bullets like this, but all I need is one. Well, I can just write it like this. There's an x bullet sequence in I such that f of x bullet equals y bullet. But now I'm going to use the same trick as before. I have a sequence in I. I know that I is a bounded interval, which means that x bullet is a bounded sequence, so that by Bolzano-Weierstrass, x bullet has a subsequence that is convergent. Let's call it x bar. Say it converges to x bar infinity. But then finally, because f is continuous, applying f to both sides, I still have a convergent sequence. But if I were to apply f to x bar bullet, that's going to give me a subsequence of y bullet. Well, I guess I don't need to go there. Let me think. There's a sequence that converges. Oh, OK, that's fine. I'm going to leave it as an exercise. If you have a convergent sequence, any of its subsequences too converge to the same point. Any subsequence of a convergent sequence converges to the same limit. Limit of the original sequence which means that since this is a subsequence of y bullet, the limit of this has to be the same thing as alpha. So that alpha is indeed in the image. And consequently, max of f exists. So you see, what makes things work is this Boson-Weierstrass. And I'm really using the property that I is bounded. Where I use closedness here is in guaranteeing that when I take the subsequence, it converges to some point, and furthermore, this point too is in I. That's where I use the fact that I is closed. In fact, I'll leave the case for min to you. It's pretty much the same argument. Instead of looking at the sup, you're going to look at the inf. But other than that, there's no other difference. Or if you want, you can apply the statement to minus f with the idea that if f is continuous, so is minus f, based on the exercise. You can do it that way too. All of these have also proofs using epsilons and deltas, but I assure you they're a lot more cumbersome to write down. You end up needing to do a lot of epsilon delta management. So somehow sequences, once you get comfortable with taking sequences and subsequences and using continuity in tandem, they end up being very useful. Just like send off a signal and the x coordinate, and then continuity of the function allows you to transform it into into convergence in the vertical direction and so on. Very pleasant. Yeah.
So for these kind of flavors of proofs, you would recommend looking for a subsequence or like any sort of sequence, and
Yeah.
eventually, because that seems to be the flavor of all this.
Well, I mean, the subsequence is not the point. The point is that I want a convergence sequence.
Yeah. Okay.
Yeah. Convergence is the best thing you can have when it comes to a sequence. The thing often is that, so for instance, here I chose a sequence that converges to the sup, but then I use the fact that the sequence is supposed to be in the image. Well, there's a horizontal sequence that y bullet comes from. But then at this point, I don't know if x bullet converges or not. See, that is not guaranteed. But I can sample out my times to get convergence still. Yeah. Yeah. Yeah, like if possible, you always want convergent sequences. And even better, if you can achieve, you want a constant sequence. Okay? Often you don't have constant, but at least you have convergent. Any other comments or questions? Okay. So that's the maximum principle, which means that if I have a closed and bounded interval, and if I have a continuous function defined on it, well, I know that it attains its max and its min, even though it's called the maximum principle because, you know, min of f is the same thing as max of minus f, so it doesn't matter that much. Now, somehow, the next theorem, intermediate value theorem, in a sense is complementary to this. Because it turns out that this theorem is not really that much about the fact that I is an interval, because when someone tells you that a certain subset of reals is an interval, they really are conveying geometric information. So interval is a very geometric idea. Okay? And in fact, instead of this, if you were to switch over to this, you would be able to bypass things like the Bolzano-Weierstrass and stuff like that. So if I have a metric space and a subset in it, I'm going to call that subset compact if any sequence in that set has a subsequence that converges to some point in that set. So this is basically the consequence of Bolzano-Weierstrass. Okay? So if you were to replace this compact subset of reals, or in fact any metric space, but let's just focus on the reals, then literally the same proof would work, except that instead of having here Bolzano-Weierstrass, here you would just use the fact that the set is compact. So you would just assume that you can go from here to here. I have a sequence X bullet in my compact subset, which means that by compactness, it is a convergent subsequence. You will sort of bypass this Bolzano-Weierstrass. But you would just say, oh, that's by definition. I'm just assuming my set to have this property. Okay? And in the first part too, when we used the Bolzano-Weierstrass, that's what we used, in fact. I took a sequence, I constructed a sequence somehow in my I, and then I passed over to a subsequence that I know converges. That's what I used. OK. So maximum principle is about really this compactness, closed and bounded part. Intermediate value theorem is about the interval property. It's a geometric property. Okay? Well, it's still not quite a geometric property, but it's more of a geometric property than this. And it says this: if I have a continuous function defined on an interval, maybe closed and bounded, maybe not, doesn't really matter, then f attains any height between any other two heights it already attains. So here's a picture. So this was the maximum principle. I have here this. It has to be defined on the endpoints. Okay. Max and min are attained. Well, or this is the extreme value theorem. Intermediate value theorem says this: if you know that f attains these two heights, then it attains any other height in between. Meaning, say on the left endpoint your function is here, and on the right endpoint the function is here. Then, even if you were to mark out a certain height in between, say this, you know that the graph of f is going to intersect with this at least one point. Maybe multiple, but at least one. Okay. So I guess this corresponds more to this idea that a continuous function has a graph that you cannot draw without lifting the pen off the paper, marker off the board. So intermediate value theorem. Okay, so this is an intermediate value in this case, for instance. I can write it like so. Let I be an interval, and y1 and y2 be two heights. So be 2 points in the image. Oh, I should take a function also. I be an interval, f be a continuous function defined on I. Let's let y1 and y2 to be 2 points in the image. So I have 2 heights. Let's say that, well, I guess I don't need to say anything. What can I say? To describe a point in between, I can take a t between 0 and 1. Then the linear interpolation of these two guys is completely within the image. In other words, 1 minus t times y1 plus t y2 is also in the image. We had seen this expression before in the definition of an interval, in fact. At time 0, you see, you're at height y1. As you're increasing t, you're going from 0 to 1. And I'm saying no matter what t is between 0 and 1, all of these heights will be attained by f. So you don't need to, you don't get to jump from height y1 to y2 without passing through every single value in between, intermediate value. Okay, that's a statement. There are other ways to state the same thing, but this is perhaps the fastest. So here's the idea. Proof. Since y1 and y2 are in the image, I know that there are x1 and x2 and I such that f of xi equals yi. F of x1 equals y1, and f of x2 equals y2. Now, there is some cases you need to worry about, but without loss of generality, we can assume that x1 is to the left of x2 and y1 is below y2. So that you have the picture, you have the following picture. So here's x1, here's x2, here's y1, here's y2, and I tell you that the function, or rather its graph, passes through this point and this point. Let's call this midpoint maybe y3. And so I have a height in between, somewhere here. I want to show that there is at least one point between x1 and x2 such that the graph of f intersects at exactly that horizontal, this red line. Here's what I can do. I can define a set which is essentially a sublevel set. Define A to be the set of all those x's between x1 and x2 such that f of x is upper bounded by y3. That's a sublevel set. Okay. Now, I know that this set is non-empty because x1 is in it. F of x1 is y1, and y1 is less than y3. So x1 is in A, and A is a subset of this bounded set. Let's write it better. Which means I have a bounded and non-empty set, which means by completeness axiom, it has a sup. And in fact, the sup is between x1 and x2. Alpha, which is a sup of A, is some well-defined number in this interval. Okay, we're almost done. We need to verify that f of alpha, in fact, is y3. Okay, we're not done with the proof, but I'm out of time, so we're going to stop here. Thank you. All right, let's start. Good morning. So today, I want to first finish the proof of the intermediate value theorem, then talk about this third theorem where both the maximum principle and the intermediate value theorem play a big role. Says something about how continuity, intervals, and monotonicity play with each other. Probably that's going to be it for today. We're slightly behind schedule, but it's not a major issue. On Friday, we're going to have our first midterm, and then next Monday, I'm going to say a couple words about convergences of sequences of functions. Okay. So intermediate value theorem basically says this. If you have a continuous function defined on an interval, and if you know that this function attains two given values, in that statement y1 and y2, then in fact the same function has to attain any other value in between. So to draw a picture, we can imagine something like this. So I is horizontal, of course, and the function, the graph of f is going to be here. Let me sort of introduce some notation here. So I start the proof here. Let's say I fixed a t in between, or rather between 0 and 1, and this in-between value I call y3. Since I know that these two heights, these two values are in the image, well, by definition, that means that there are 2 points, x1 and x2, in I, such that f of x1 equals y1 and f of x2 equals y2. And then here, there are a couple different situations, but without loss of generality, we might assume that x1 is to the left of x2, and indeed, y1, y3, and y2 are positioned this way. So, given all this, the picture we have is something like so. Okay, I could be a larger interval, but at the very least, it has a smaller subinterval from x1 to x2. And at x1, f is at height y1. At x2, f is at height y2. And in that expression, as time goes from, so as t goes from 0 to 1, I'm really spanning or scanning from height y1 all the way up to height y2. But you know, in this definition, I'm not really, so in the statement, I'm not really requiring that t is strictly between 0 and 1. But in that case, I already know that if t were either 0 or 1, I already know that this expression is already in the image. That's why, without loss of generality, I'm assuming that t is some number strictly between 0 and 1. So that y1 is strictly less than y3, which itself is strictly less than y2. In any event, here is the height at y3. So far, what we did was this. We defined the set A, the set of all those x's between x1 and x2, such that f of x is upper bounded by y3. If you want to use this more compact notation, you can think of this as the intersection of this interval with the preimage of this interval under f. To connect it to week 1 notation. And more generally, sets like this are called sublevel sets. It's a sublevel set of f. So if this was an equality, this would be a level set. But since this is an inequality, this is called the sublevel set. Not that it's very important what you call it, of course. Then we realized, well, f of x1 is y1, and y1 is strictly less than y3. In particular, it has to be within A. So x1 is in A, and by definition, A has to be a subset of x1, x2. Again, here, really, I can say that x2 is for sure not in A, because f of x2 is some value that exceeds y3. So A is a subset of this half open, half closed interval, if I want. In any event, this means that A is a non-empty subset of reals that happens to be bounded, which means that by the completeness axiom, I know that for sure alpha, which is a sup of A, is a well-defined real number. OK. The claim, of course, is that f of alpha, which is a well-defined thing, is exactly equal to y3. So what is this sup of A, in a sense? Trying to visualize, we want to use this intuition that continuous functions are those functions whose graphs are sort of continuous in a sense, right? So the graphs of continuous functions you should be able to draw without lifting the marker off the board. And I know that I start here and I end up here. So it's going to go up and down, possibly. Maybe it's something like this. Maybe it's something like this, in which case there's exactly one x value where f of x equals this specific height. But in principle, it can go up and down multiple times. So you might see something like this, perhaps. Maybe there's an interval where it's exactly y3 and so on. And then this happens. Okay? The graph of f could look like this. In which case, the set A we could visualize like so. I'm looking at the sublevel set. So I need to include everything here. Then it's above. Now it's below again, and so on. So for instance, this part I need to get rid of. Then this little hill, and this part. Everything, and this I have to get rid of as well. But you see, this A set, even though it's sort of like a sublevel set, it's not just one interval. It's more complicated, possibly. And how can I visualize this A, or this alpha, the sup? Well, you can think of it like this. Collapsing the time parameter, you had a one-dimensional motion, and you started at this point. And you're sort of moving around, up and down. You're in one dimensions. And so somehow, say, this is y1. Somewhere here is y3. Oh, sorry, y2. And then in between somewhere is y3. And so now I'm f, OK? I'm the function. I started here. And I do this, and I do this. Maybe I sort of dip a little bit, and then do this, come back, and so on. Alpha, intuitively, is sort of the photo finish, where I reach y3 for the last time, and then I don't look back. This is the last time I'm going to go past y3, and then beyond that, I'm just going to not look back. I'm not going to return or anything. OK? That's sort of the intuitive way to visualize this. So we use such sublevel sets quite often. Of course, it's an art in and of itself to realize that, oh, this is a set that you can look into. And the sup of it is going to give you the specific x value you need. OK? That's where the sort of creativity comes into play. Any comments or questions about this so far? Okay. And another issue here is that it's useful to draw caricatures like this, but in a sense, it's a double-edged sword, because to draw a caricature to figure out what you should be doing in the proof, well, you're gonna need to draw something that already works. But then it gets confusing. What is there to prove? Well, what there is to prove here is that somehow, even though this caricature has to do with what we're trying to do in the proof, you should be able to look at the caricature and use it without necessarily using the fact that you're trying to prove. So it's a bizarre thing. It's like you have to look at this, and you have to not take into account that I drew this graph without lifting my marker off the board. So because of this issue that, when you're trying to develop intuition, you end up confusing what needs to be proven with what is already known. Some instructors for classes like this, they would draw no pictures whatsoever, okay? Because this is not a rigorous thing, and they would say, I'd rather not get confused as to what is being proven and stuff. So when I was first learning this course, when I was first taking this course, my professor was against all sorts of pictures. Everything has to be sort of completely rigorous and so on. I disagree with the sentiment. You see, things get a little murky, in terms of logic and what needs to be proven and so on. But I still think it's important to develop the intuition and perhaps realize or figure out how to use these more intuitive pictures, and always take them with a grain of salt. Okay. So I have this alpha so far. The claim is f of alpha equals y3. So that, indeed, y3 is in the image. So we need to do two things. When you're trying to show the equality of two numbers, you show one is less than the other one, and vice versa. So first, I can take a sequence, a bullet in A, that converges to alpha. Okay? I'm going to leave this to you if this is not clear to you, but all you need to do is to farm the definition of the supremum to come up with a sequence like this. You're going to take 1 over n, for instance, and then you're going to say alpha minus 1 over n is not the sup by definition, because it's a number lesser than the best upper bound, which means that there has to be some point in A that exceeds alpha minus 1 over n. And then as you take n to infinity, this alpha sub n is going to go to alpha. So I'm going to leave that to you. But then f of alpha, which I can write like this, I'm subtracting and adding the same term. If you want, I can write it like this. Thus, for any n, f of alpha is equal to this. But then this is some number, which means that if I were to replace it by its absolute value, that would only increase. And since I know that a bullet is a sequence in A, f of a sub n is upper bounded by y3. Because that's the definition of what it means for something to be in A. But then this goes to 0 as n goes to infinity. And this is y3, which means that if you were to take n to infinity, you would get that f of alpha is upper bounded by y3. Okay, this is the one side. So I need to show the other way around too. Instead of showing that f of alpha is greater than or equal to y3, I'll say, I'll suppose that f of alpha is strictly less than y3, and then try to come up with a contradiction. Next, suppose f of alpha is a number strictly less than y3. I want to come up with a contradiction which is going to allow me to conclude that f of alpha has to be equal to y3, in fact. OK. Here's what I can do. I know that f is continuous. It's a hypothesis. And since f of alpha, I'm supposing, is some number strictly less than y3, that means that their difference is a positive number. Which means that that positive number I can use as an error margin in the definition of continuity. OK? So then, y3 minus f of alpha, and if you want, I can even divide it by 2, is a positive number. Since f is continuous, this is a faster way of writing f is continuous, at alpha if you want. I know that, I'll continue here, there is a delta such that for any what do I want to do? OK, I'll leave it like this. There's a better way to write this, and there's a minor error in what I'm going to write, but I'll let you figure out what that is. For any x in the open interval, if the distance between x and alpha, well, I guess there's no mistake at this stage, actually. Yeah, I'm all good. Implies f of x minus f of alpha is upper bounded by this error margin, y3 minus f of alpha divided by 2. 3, 2, doesn't matter that much. OK. I'll just draw a picture. Again. So y1, y2. We had a y3 here. I had assumed that f passes through this point and through this point. I did some stuff and came up with alpha here. And at this stage, I'm assuming that f of alpha is less than this. So I'm assuming that instead of f passing through this intersection, it passes through this point. OK? That's what I'm assuming. Now I'm using the definition of continuity of f at this point. You see y3 minus f of alpha is this aperture over here. And I halved it. And I'm using that as my error margin. So it looks like this. For this error margin, continuity tells me that there's a delta such that if I'm within a delta of alpha, maybe like this, so alpha plus delta, alpha minus delta, okay, then the image of any point in this orange small interval under f is going to land into this small box with two sides orange, two sides green. only thing I should be careful about is, well, in principle, this delta may be to the right of x2. So what I can do is I can cook up some x value to the right of alpha such that everything still works. So for instance, and I'm going to call that x star. Then for x star equals alpha plus, what do I need? I can add some small number to alpha to get this x star. Maybe delta over 2, or the difference between these two guys divided by 2. To guarantee this both, we can just add the min of both of them. That's a well-defined real number. Satisfies this property, which means that f of x star, when you rearrange, we get that it is still, well, you take this to the other side. I'll just do it once, like this. But then since y3, we're assuming is, or rather, f of alpha, we're assuming to be strictly less than y3. If I were to replace f of alpha here with y3, this would increase, and I would get this. Meaning, I have x star in A, but that cannot happen because x star is a number strictly greater than alpha, and alpha is supposed to be the soup. And that's how we finish the proof. So here, to come up with this specific expression, you need to do some calculus type of inequality type stuff. But apart from that, the rest is just using the definitions. Yeah.
So I'm confused about the set A.
OK.
What is the set A? Where did you define that? Because you're saying that
I'm defining it here.
oh, it's up there. Such that oh, okay. I must have just missed that.
Yeah. Yeah. Comments, questions? Yeah, so this is part of why analysis proofs are perhaps they're of a different flavor. Some people really dislike the flexible aspects of proofs like this. So for instance, I needed certain bounds, but the specific shapes or specific expressions in general don't really matter that much. So for instance, I said, oh, suppose f of alpha is strictly less than y3. Instead of dividing here by 2, I could have divided it by pi if I wanted. Doesn't matter. What does matter is that this is a positive number that I get to use within the definition of, I get to use as an error margin for the definition of f. I'm using this as the so-called epsilon. Right? For any epsilon, there's a blah, blah, blah. I'm saying, oh, if for any epsilon, there's a delta epsilon thing, I can choose epsilon to be this specific thing. Why do I choose this? Well, so that I know ultimately that even if I exceed this alpha, I still have some leeway to go. I still have some sort of flexibility to move to the right, and I will still not reach this y3. How do you come up with these things? It's like it's based on experience ultimately. You sort of study proofs that are similar, and you eventually develop your own methods, in a sense. Comments, questions? Okay, so that's that, intermediate value theorem. Next up, we connect all of these, and we get one big theorem. And when you're reading a proof from in the textbook and stuff too, I would highly recommend you start drawing the picture. It's going to make a lot more sense once you can sort of visualize what is really happening. So, theorem. It has 3 parts. Let's let I be a closed and bounded interval. So I'll just write it like this. I is lambda to rho, like so. In principle, it could be just a singleton, a set that contains only one element, but it doesn't matter. F be a function on I. At this stage, I'm not going to say it's continuous, because one part of this theorem is going to be blah, 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 then f is continuous. And so I'm just going to take an arbitrary function. Remember, instead of writing it like this, I could have said, let f be a function taking real values defined on I. I'm just using this notation. Then, this has 3 parts. Somehow the second part is the hardest. But in order to prove the third, we're going to need the second part. So I think this is the best way to state them. If f is continuous, then in fact I can say the image of f looks like this. It's a closed and bounded interval from the min of f to the max of f. Okay. Second, if the image of f is some closed and bounded interval, and f happens to be strictly monotonous, then in fact f is continuous. And f is strictly increasing or strictly decreasing. Decreasing. Then f has to be continuous. And finally, if f is continuous and strictly increasing, then in fact, it's a homeomorphism, and the inverse of it is also either strictly increasing or strictly decreasing, depending on f. And is strictly increasing or decreasing. then f is a homeomorphism. So I can just write it like this. F is a homeo from I to the image. What is a homeomorphism? We had defined this before. Homeomorphism basically means, well, f inverse exists as a function, and it itself is also continuous. So I'll just write f inverse is a continuous function. That's what that means. And what does it mean for f to be strictly increasing? Well, it means if you feed to it two x's, one strictly to the left of the other one, then f has to be has to preserve sort of this relationship. Okay, that's what strictly increasing means. Decreasing means this sort of turns the other way around. If you want, you can kind of visualize this strict increasing as sort of positive derivative. The problem with that is that at this stage we haven't defined the differentiability, and in principle, f doesn't even need to be differentiable, actually. So this is really the proper way of thinking about strict increasing, which, in a sense, is fully compatible with this strict increasing function j that we were using for subsequences. It's the same notion. Okay. Let's do 1. 1 is the easiest to prove. 2 is the hardest to prove. 3 is, again, not that hard once we have 2. Now, I should mention, somehow this theorem is essentially why single variable calculus is so much more easier than multivariable. The point is that in multivariable calculus, there is no analog of a theorem like this. Because imagine thinking of a function defined on the plane, taking values in the plane, or between the complex domain itself. Well, you can't even make sense of strictly increasing and decreasing at this stage. So monotonicity already is a problematic notion in multivariable. Another thing, too, is, well, it's not super clear what nice sets are in multivariable. Maybe they are rectangles and so on, but that gets problematic, which those of you who are going to take the SQL class 30 to 20 are going to need to worry about quite a bit. But in single variable, things are really nice in a sense. Intervals, increasing property, all that stuff allows you to say a lot of things. So, 1. Now, I is a closed and bounded interval. F is continuous. Which means, by the maximum principle, min of f and max of f are well defined, and indeed they are specific values in image. So, by the maximum principle, min of f and max of f are 2 points in image. That's what maximum principle says. Any continuous function defined on a closed and bounded interval attains its min and max. But then, I is an interval, f is continuous, which means, by the intermediate value theorem, f has to attain any other value in between these two. So if you have this and this, both in image, that means that the whole closed and bounded interval with endpoints, these two, has to be within it. Okay. Well, we have one side of the equality. We show that this right-hand side is a subset of the left-hand side. How can I argue that the other way around also works? In other words, the image is inside this closed and bounded interval. Any ideas? So for item 1, I'm trying to show that this set is equal to this set. Well, how do you show two sets are equal? You show one is included in the other one and vice versa. So far, we were able to show that this guy, right-hand side set, is a subset of the left-hand side set. But for equality, I also need to argue somehow, that the left-hand side set is a subset of the right-hand side set.
Isn't it just the case by definition of minimum and maximum?
Essentially, yeah. Yeah. Because min of f is nothing but the inf of image of f by definition. And likewise, max of f is nothing but the sup of image of f. But for any subset of reals, we know that the closed and bounded interval from inf to sup is the smallest closed interval that contains the set. So by problem, I don't remember the number, but from the previous problem set, I'll just write it explicitly. Inf of image of f, sup of image of f, but then this is nothing but min and max. Oh, this is the end of the proof for 1. I'll just put a check mark here. Rather pleasant. So you see, one side of this course is going to be building up the technology. We're going to sort of spend time in class proving things. You're going to spend time by yourself, by your colleagues, verifying or proving certain statements. And then we're going to start using them. We're going to just refer to the things that we have established to do other things. Okay. Let me pause the proof of 2 for now. Assuming 2, let's prove 3. Okay. Then we're going to go back and prove 2 also. I just want to get 3 out of the way. That's because the proof of 2 is somewhat involved. And when you're reading things too, in math literature, typically you would see this. People would say theorem A, B, C, and D. Let's assume A, B, C, and first prove D. So even though, they write the statements in a certain order, sometimes it's better, perhaps, or the author, for whatever reason, decides to prove things the other way around. So I'm going to assume 2. Assuming 2, I'm going to prove 3. So proof of 3, assuming 2. And once I'm done with this, I'm going to prove 2 also. I'll just do it like this. OK, so let's assume 2 is OK. Meaning, if I have a function that is strictly increasing, whose image is a closed and bounded interval, let's suppose that I get to conclude that this function has to be continuous. OK. Now I want to show 3. Suppose if it's continuous and is strictly increasing. The decreasing case, again, is pretty much the same idea. I'm just going to do one side. Now, any strictly increasing function, I'll leave that to you as an exercise, is onto its image. Therefore, it has a functional inverse. Okay? Then I don't know what image of f is, so I guess I know that it's an interval also, but it doesn't matter. Image of f to I goes back, exists. And it's also strictly increasing, and is strictly increasing. Okay. This is a week 1 exercise. But then I have then f inverse is some strictly increasing function whose image is an interval. I started with an interval. So by 2, I can conclude that f inverse has to be continuous. But that's what it means for f to be a homeomorphism. It has an inverse, and the inverse is continuous as well. Is a homeomorphism. Let's try it. Homeomorphism. Okay. So that's the end of the proof of 3. Proof of 2 is the most involved. Okay. Let's think about this. Let's draw a picture first. Suppose f is a function, its image is an interval, and it is strictly increasing. Okay? Let's start with writing down the assumptions. So suppose image of f is an interval and f is strictly increasing. Here's the picture I have then. Okay. Something like this. Lambda to rho is my domain interval, I, and the heights go from L to R. Since I'm assuming that f is strictly increasing, it must be the case that f of lambda is L, and f of rho is R. Okay. What I assume for the second part is that somehow the graph of f intersects any horizontal line between L and R. Somehow, though, I need to assemble these intersections to come up with a nice continuous pattern. That's what's at stake. Well, we want to show, that is to say, that f is continuous. What does it mean for a function to be continuous? It means it is continuous at any point. Let's try to argue by contradiction. Suppose it is not continuous, meaning suppose there's at least one point where f fails to be continuous. In other words, we'll go like this. For a contradiction, suppose there is an x star in I such that f is discontinuous at x star. F is I have 5 minutes. OK. We'll keep pushing then. Now we need some actionable thing. This is where you can use this logic business where you can negate. In the textbook, they use the epsilon delta stuff. I'm just going to use a sequence definition. I find it more convenient. How can I sort of open up what it means for f to be discontinuous at x star? So we have the notion of continuity. So you want to take that and you want to sort of negate the whole thing. Okay. I'll give you a couple minutes to think about this. Yeah.
Isn't to be discontinuous that there exists an epsilon such that some point in the sequence it fails, it's greater than epsilon, something in sorts?
It fails to be less than epsilon, but yes.
Right.
Yes. This is, you see, that's why I spent so much time with logical things. You're going to see something like this, but you want an actionable sort of statement out of this. You cannot just use discontinuity as a word. You need to turn it into math. You can use the epsilon delta stuff. I'm going to use the sequence stuff. And I'm going to say that means there is at least one sequence in I that converges to x bullet, or rather x star, whose image sequence, f of x bullet, fails to converge f of x star. So there is a sequence, let's say x bullet in I, such that x bullet converges to x star. However, f of x bullet fails to converge to f of x star. Remember, f would be continuous at x star if any sequence that converges to x star would be transformed to a sequence that converges to f of x star. So I'm saying, in order for then f to be discontinuous at this point, there has to be at least one exception to this rule. And that exception is this x bullet, I'm saying. Okay. So in our picture then, I have a sequence, horizontal sequence here, that sort of zeroes in onto x star as time goes by. But somehow, if I were to look at f of x star, the height at f of x star, and where f takes each of these terms in the sequence, then I have a vertical sequence, but eventually that has to stay away from this target. So somehow, what ends up happening is going to be, well, if I were to look at the images of all of these heights is going to stay away from this orange band. Okay? Now, at this stage, it's not super clear as to how we're going to use this strict increasing property for f, because you see, we don't know f is continuous, so we don't have much to use. But one thing we can do is we can sample out a strictly increasing or strictly decreasing subsequence. And then we're going to be able to use that subsequence in tandem with the strict increasing property of f. Okay? So we still have a couple of things to say about this part of the proof, but that'll be it for today. We have the midterm on Friday, and then we'll continue from there. Thank you.